My YouTube channel. In this video lecture, I will discuss from Halliday, Resnick, Krane, chapter number 35, that is magnetic properties of material. I will discuss MCQ solution of question number 1 to question number 9. So let's begin. Question number 1 is, a magnetic dipole is oriented in a uniform magnetic field so that the potential energy is a maximum. The magnitude of the torque on this dipole will be maximum, minimum, or it's depend on the source of the magnetic dipole. So if we know the potential energy of the magnetic dipole, it would be like U is equal to minus mu dot P, where mu is the magnetic dipole moment and V is the magnetic field, where when we open this dot product we get mu d cos of theta, where theta is angle between mu and V. So we know that U has largest value when mu and V both are anti-parallel to each other, like this one here. B is in this direction where mu is in opposite direction. So angle between these two is 180 degrees. So you get U is equal to plus mu V. That would be the maximum value of the potential energy. Now in this situation, what could be the magnitude of torque? We know the formula of torque, that is mu cross V. When we open the cross product, we get mu V sine of theta. So theta is the 180 degree in this situation. So sine of 180 degree is 0. So the torque would be minimum in this situation. Here option B is the correct option. Now question number 2 is, a simple bar magnet hangs from a string as shown in figure. A uniform magnetic field B directed horizontally to the right is then established. Which of the pictures shows the equilibrium orientation of the bar magnet? So in the diagram, the first one A, in which there is no application of magnetic field, but in the B diagram magnetic field is applied in this direction horizontally. So what would be the equilibrium position for this bar magnet from A, B, C, D, E? We have to select only one option. I have drawn the magnetic field in the right direction horizontally like this one. So as we know that the equilibrium is established whenever the potential energy is having its minimum value. So its minimum value could be when the theta is the 0 between mu and the B. As we know that the direction of mu is towards the north, like this one here. In this direction would be like this one here in this direction. So whenever we just simply apply the magnetic field, then the bar magnet tries to align itself such that the direction of the mu is in the direction of magnetic field, external magnetic field. So although this bar magnet tries to align itself exactly in the direction of magnetic field, but because of this string just forcing it from the perfect alignment in the direction of B, so option C could be the correct option, in which the string is taking the bar magnet in this direction, but the bar magnet is trying to align itself in the direction of B. In addition, in uniform magnetic field, we know that the net forces are 0 there, but in uniform magnetic field, but the net torque is not 0, so torque actually tries to align mu with magnetic field. So option C is the correct option. This one. Question number 3 is, a magnetic dipole is in the non-uniform magnetic field. The dipoles will always be attracted to the region with a stronger magnetic field, always be repelled from the region with a stronger magnetic field. Option C is might be repelled but will eventually flip over and attract to the region with stronger magnetic field, might be attracted but could flip over and then be repelled. So whenever there is magnetic dipole in a non-uniform magnetic field, it's always attracted to the region with stronger magnetic field. So option A is the correct option. MCQ number 4 is, for distances d much larger than dimension of the magnetic dipoles, the force between two dipoles is proportional to d raised to power minus 6, d raised to power minus 4, d raised to power minus 3, or d raised to power minus 2. The situation is similar to two dipoles and there is a distance between them is d. Let's suppose it's not x, it's d, and the magnetic field due to the dipole is inversely proportional to the distance between the two dipoles, and it's x raised to power cube or d raised to power cube. And the formula for interaction energy of the two dipole is minus m dot b. So we can say that the potential energy for two magnetic dipole can also be directly proportional to x raised to power -3. And we know that the potential energy and force are related, and with this formula F is equal to minus du by dx. If we take its derivative with respect to x, then we get x raised to power -4. So it means that force is directly proportional to x raised to power -4. If we replace x with the d as distance between two magnetic dipoles, so force is directly proportional to d raised to power -4. It means that option B is the correct option. Question number 5 is, which of the following does not significantly contribute to the magnetic properties of a substance? Option is orbital magnetic moments of electron, or spin magnetic moments of electrons, or magnetic moments of protons and neutrons, and option D is all contribute equally. This point is mentioned in Halliday Resnick Krane book in the topic of atomic and nuclear magnetism, in which it is mentioned that the nuclear magnetic moments are very smaller than atomic dipole moments. So because of the fact that they are approximately less than order of units power -3, so their contribution to magnetic properties of the material is negligibly very small. So it means that option C is the correct option, that we usually neglect the contribution of magnetic moments of protons and neutrons. Option C is the correct option. Question number 6 is, what are units for the magnetization? Tesla per meter cube, or coulomb per meter second, and coulomb per meter per second. So here is the solution, as the magnetization is defined as its actually net magnetic dipole moment for a material per unit its volume. And we know that the magnetic dipole moment is equal to the current into the area of the loop. So by considering these two definitions, we can write mu as Ia, where the unit for I is ampere and area unit is meter square, where volume unit is meter cube. So it could be area per meter, but in option it's not given, so we have to convert it into some possible units. That's why I multiply and divide it with the second. So ampere second by meter second, as we know that the ampere second is equal to coulomb by this definition, as the current is a flow of charge. So the charge could be written as it, where the unit of I is ampere and the unit of time is second. So ampere second could be written as coulomb here. So coulomb per meter second is the unit, another unit of magnetization. So option C is the correct option, that is coulomb per meter second. Question number 7 is, which type of substance has the largest atomic dipole moments? Paramagnetic, diamagnetic, ferromagnetic. Paramagnetic and ferromagnetic substances tends to be about the same, whereas diamagnetic substances have no permanent magnetic dipole moment, or all three types are about the same. Diamagnetic substances do not have any atomic dipole moments, only ferromagnetic and paramagnetic have, and ferromagnetic having the largest atomic dipole moments. So option C is the correct option. Question number 8 is, what happens when a paramagnetic substance is placed in an external magnetic field? The atomic dipole moments weaken slightly but used to line up with the external field. The atomic dipole moments strengthen slightly and tend to line up with the external magnetic field, or the atomic dipole moments weaken slightly and tends to line up against the external field. The atomic dipole moment strengthens slightly but tends to line up against the external field. For paramagnetic substances, option B is the correct option. The atomic dipole moment strengthens slightly and tends to line up with the external field. This is not happen in any case, option A, and option C is happens in the case of diamagnetic substances. So the only option for paramagnetic substances is option B. Question number 9 is, a small cylindrical ball magnet has a diameter of 1 cm, length of 2 cm, and a dipole moment of 5 Joule per Tesla, assuming the magnetic field were produced by a single current loop. So about how large the current would be. You can solve this problem by this formula, as we are given diameter, so you can get radius by dividing diameter with 2, as well as you are given length. So from this information you can get area. Then after that you can get magnetic dipole moment, that is I into area of the loop. So I is equal to mu by A. That's all for today.